Right, but what makes it a polynomial versus like not a polynomial? So what makes it a polynomial is that it's basically comprised of terms with variables that have exponents which are positive integers. So x to the 1, x to the 2, x to the 3 are okay, but not x to the negative 2 or not x to the 1 over 2, okay? And if that's the case, right, that's what makes it a polynomial function. If that's the case, then the leading coefficient is a to the n, right? And that's the coefficient of the variable with the greatest exponent. So, so take a look at these, okay? The highest exponent in the polynomial function determines its degree. So if the degree is 0, that's like f of x equals, let's say 3, you have a constant function. If the degree is 1, then you have a linear function. If the degree is 2, then you have a quadratic function. Let's do this now. We'll do that later. Okay. So let's take a look at what graphs of polynomial functions look like. This first one is an example of a polynomial function because it is defined and continuous for all numbers, and it's smooth, rounded turns. Versus, for example, the second one, this is not continuous for all of the x values, right? There's clearly a jump discontinuity there. This next one is continuous, but the fact that there is a corner here and it's not a round turn, that makes it not a polynomial function. Okay? All right. So, yep.
If you have x squared plus absolute value x.
No absolute values.
It can't be anywhere.
No, yep.
I know a line wouldn't be considered a polynomial function.
It is.
Oh, it is?
Yep, right here, right? So a polynomial is something where you have x's raised to integer exponents. X to the 1, x to the 2, x to the 3, x to the 4. Not 1 over x, not the square root of x, not the absolute value of x, not x times y, okay? Okay, so we know that from before, graphs of even degree polynomial functions are like x squared. Graphs of odd degree are like x cubed. So if I wanted to graph, 4x to the 6, we did this last time. We know exactly how to do it. X is 0. When x is 1, I get 4, and so on, right? And this will be just like super thin going up. And then this one, this is a cubic function, shifted right 4 up 1. And then it's a cubic function, meaning if I go over 1, I go up 1 cubed. If I go over 1, I go down 1 cubed. So, this is what this is going to look like. Okay, now, we really want to get past this and talk about the leading term test. So the leading term for a polynomial function is the term with the highest exponent, right? So if you take the leading term, right? Suppose, so it's like ax to the n, where n is the exponent, okay? Suppose n is odd, then we know that the end behavior are going to be opposite. One side is going to have an end behavior of positive infinity. The other side is going to have an end behavior of negative infinity. So that is determined by a, which is the leading coefficient, okay? So for example, if your leading term is 3x to the 5th, okay, this a is positive. So as you approach positive infinity, f of x goes to positive infinity. As x approaches negative infinity, f of x goes to negative infinity. But if a is negative, so if you had negative 3x to the 5, then it is the opposite direction. So as x approaches infinity, f of x approaches negative infinity, and then it's opposite on the other side. However, suppose the leading term has even exponents, right? So suppose the leading term is 3x to the 4. Then we're not concerned with what happens in the middle. We're looking at the end behavior. Both at positive infinity and negative infinity, this would go up to positive infinity. And suppose a was negative, so like negative 3x to the 4. At both ends, it'll go to negative infinity. Okay, let's just do one here. So this is an example of a polynomial function. Do you see how you basically just have the independent variable that has exponents which are positive integers? Okay, now we want to describe the end behavior using the leading term test. We first take the leading term. Now this is 3x to the 4. If it's 3x to the 4, if it's an even exponent, x to the 4, both ends are either going to go up to infinity or down to negative infinity. And that's determined by the positive 3, right? So here we say the limit of f of x as x approaches infinity is infinity. The limit of f of x as x approaches negative infinity is also infinity. So the graph of this, now I'm not concerned with what happens near the origin, but towards the end, it's going to go up to positive infinity on both sides. Okay? Okay. This one, the leading term, be careful, this is not written in standard form. This is the leading term. So it's negative 2x to the 5th. Now, by virtue of it having an odd exponent, we know that one is going to go to positive infinity, one is going to go to negative infinity. So I write down my skeleton. And it's probably easiest to look at the positive infinity side. At the positive infinity side, x's are positive. So if you have a positive x here, y will be negative, correct? So this will be negative infinity. And since it's an odd exponent, this will be the opposite, positive infinity. If you don't believe that, just put in a negative 1. Negative 2 times negative 1 to the 5th is a positive number. Okay? All right. That's end behavior. Let's talk about x-intercepts. So we know that x-intercepts is the same as the zeros, the roots, or the solutions. To find x-intercept, set f of x equal to 0 and solve. Now, here, sometimes I feel like because we're always like, solving manually, sometimes we forget exactly like what we have at our disposal, right? So if f of x is, I don't know, x squared plus 4x, we're just going to set that equal to 0 and solve it, okay? We can do this by hand, no problem. Now, if f of x is 1.6 x to the 7 minus 3.2 x to the 9 plus 4. To get the x-intercepts, you set this equal to 0 and solve it. Okay, you can't do this by hand, so how do you do it otherwise? Okay, what about the calculator? What do? You graph it and you look for what on the graph? The x-intercepts or the zeros. Exactly. Okay, sometimes like even in AP calculus, students are like, we can't solve that. It's like, no, like graph it and solve it. So remember that those two are the same. Okay, so those are the x-intercepts. Next, what we're going to talk about are what we call turning points. Guess what turning points are? They're points where the graph does what? Turns. They're points where the graph turns. So we don't say the graph turns, we say the function changes from increasing to decreasing and vice versa. So if you know the degree of the polynomial, which is the highest exponent in the polynomial, okay, then the polynomial function will have at most n distinct roots. So if the degree of the polynomial is 5, it will have at most 5 roots and at most n minus 1 turning points. Memorize that like you've memorized your name. So take a look at this. This is f of x. This is the degree. That means f can have at most 6 real zeros and at most 5 turning points. Why 5? 6 minus 1. Now, the key word is at most. It can have 4, it can have 2, it can't have 7. Okay? So, take a look at this one. The actual graph of this, when you graph it, looks like this. So, in actuality, this actually has how many real zeros? 3 real zeros. 1, 2, 3. And how many turning points? 3 turning points. 1, 2, 3. And that's okay. It can have the same number of zeros as turning points as long as this is less than 6. Does that make sense? Okay. Okay. So this one, state the number of possible real zeros and the turning points, then determine all of the real zeros. So how many possible zeros?
3.
Right. And how many turning points? 2. That's the maximum, right? Okay. Then it says to determine all of the real zeros. So we're going to set this equal to 0. Factor out an x. X squared plus 5x plus 4 is equal to 0. X plus 4, this is like so algebra 2, right? So x is 0, x is negative 4, x is negative 1. So it does in fact have 3 real zeros. Okay?
We only know that it can be.
You really have to raise your hand. Yep.
What did you write for that?
Turning points, TP, turning points. Okay, because
How did we know that?
I don't know. You gotta look at the page before. Okay, so how many possible zeros here? 4. How many turning points? 3. Now, we're going to factor this. Remember, this is in quadratic form. I've given you like a prompt here, but this is just because it's the notes, right? So the way we're going to factor this is it's going to be x squared and x squared. 2 numbers that multiply to 15 and give you 8. Yes? So x squared minus 3 equals 0. X squared minus 5 equals 0. Here, x squared equals 3. What's x equal to? Plus or minus root 3. So x squared equals 5. What's x equal to? Plus or minus root 5. So notice 4 real zeros. Okay? All right, this one. How many turning points?
3. 4 zeros.
4 zeros, 3 turning points. Okay, let's go ahead and factor this. So x to the 4, it's going to be x squared equal to 0. If you're solving, you must say equal to 0. And then what's this? It's negative 3 and negative 1. So x squared minus 3 is equal to 0. X squared equals 3. x is plus or minus 3, root 3. Oh, you know what? I wish I had factored it some more. Here, I'm going to factor it some more, because what if I asked you to do that? Yeah, it's x squared minus 3, and then x plus 1, x minus 1 is equal to 0. So from here, I get x is plus or minus root 3, but then from here, I get x is plus or minus 1. Okay, you know what? I'm going to add a fourth one here. I'm going to add f of x is equal to x squared plus 10x plus 25. This has how many maximum zeros? And how many turning points? Right. Okay. It doesn't matter. I don't even think that's an official abbreviation, but it's fine. So here we go. Let's do this. X squared plus 10x plus 25 is equal to 0. Okay, this factors as x plus 5 squared is equal to 0, right? But technically, now when we factor it, because we're like almost adults, this is how we factor it. But we know behind the scenes, this is x plus 5. X plus 5 is equal to 0. From each of these, I get x equals negative 5. But I'm not going to write it twice. I'm only going to write it once. X equals negative 5. So do you see how it has 1, 0, but technically it's 2 of them, right? Because it appears twice. Okay, so now that is going to make a difference. In this case, I have 4 different zeros. Plus 1, minus 1, plus root 3, minus root 3. So those are the 4 zeros. Here, I have x equals negative 5, but that's technically 2 zeros in 1. But so let's see if there is a difference when that happens. There actually is a difference. What we found here with the x equals negative 5 is it has a repeating 0. The 0 repeats. If a function has repeating zeros, the multiplicity is the number of times a 0 repeats. So, if a function has an x-intercept of even multiplicity, so in this case, we would say this has a multiplicity of 2 because it occurs twice. If it has an x-intercept of even multiplicity, then the graph touches the x-axis at that point and turns around. What do we mean by that? So take a look at this, okay? How would we graph that? Back in the day, when you had f of x is equal to x plus 5 squared, we knew that's a parabola at a vertex at negative 5, and it looked like this. Do you see that? So this one has a 0 at negative 5. That 0 at negative 5 has a multiplicity of 2. That's an even multiplicity. It means the graph touches the x-axis and turns back around. It does not cross the x-axis. But also, if it comes to the x-axis as a positive value, it stays a positive value after the 0. So it does not change sign at that point. However, if there is an x-intercept of odd multiplicity, the graph crosses the x-axis at that point, and f of x changes sign at that point. So if there was odd multiplicity, the graph would cross at that point, and if it came as positive, it would leave as negative. Okay? Let me do a couple and then I'll take questions. Let me do this example. So take a look here. We're going to graph this, okay? Or closely, like we're going to do an approximation of a graph. using A through C. So first we want the leading term test. What is the leading term here? Okay, it'll be to the 4. So take a look. X times 3x times x squared. This will be positive 3x to the 4. So that means the limit of f of x as x approaches negative infinity is infinity, and the limit of f of x as x approaches positive infinity is also infinity. So on both ends, this is going up. Okay. B, I want to find, the y-intercept. What's the y-intercept? Yeah, the y-intercept is f of 0, which is 0 times 3 times 0 plus 1 times 0 minus 2 squared. So that's just 0. Okay? And then the zeros are, since this is like factored for us, it's easy. You have x equals 0, x equals negative 1 over 3. But then you also have x equals 2. But how many of those x equals 2's do you have? 2. So here I write multiplicity of 2. Okay? MULT, multiplicity. Okay, now listen. Only if it's multiplicity of 1 are you allowed to not write it. It'll be understood that it's 1. Any other time you have to write it. Okay, now let's plot all this. So the zeros are 0, negative 1/3, and 2. Both ends are going to be up here. Okay? The one with a multiplicity of 2 is this last one. The first two have a multiplicity of 1, which is an odd multiplicity. So when the graph comes to one of those points, is it going to cross or turn around? Cross. So from here, okay, it's going to come down. It's going to cross, go back up, cross, go back up, come down, not cross, and go back up. So that's how it looks. Now I know your next question is going to be, how do I know how high or low to make these turning points? You don't know. You're going to estimate. Okay? What I will be looking for is that there is a turning point here. There is a turning point in between these two x values. And then here we go. So take a look. This, right? Look at how closely, what a close approximation of the graph we were able to do, right? Like previously, we would never have imagined that we could do this, right? So that's really cool. Okay, now questions. Yep. Correct.
And then there's something else that's at the top of the page, like zeros, points. If you ask for a root or solution,
Yeah, x equals whatever.
So only if you ask for the x.
Yeah. Exactly. Okay, so now let's do this one. This one's not factored. If it's not factored, the leading term is more obvious. So the leading term. So look, before today, you would never have been able to graph this by hand. But today we will be able to, right? So let's take a look. The leading term is negative x to the 4. So the limit of f of x as x approaches negative infinity will be what? Right, and what about the other one? Also negative infinity. Okay, good. Okay, see you. Good luck. Okay, so let's do B, the y-intercept. What is it? 0. And then the zeros, let's factor out a negative x squared. So I get x squared minus 4x plus 4 equals 0. This is x minus 2 squared. So what do I get from here? X equals 0, multiplicity of 2. X equals 2 of 2. Okay, so 2 zeros, 2 multiplicities. But look, 2 zeros, each with a multiplicity of 2, that's a total of 4 zeros, which goes along with the degree, right? Okay, so yeah, so here we go, 0 and 2, and the leading, the end behavior is negative infinity for both, right? So here, we're gonna go up, turn, go up, turn, and go back down. See how cool that is? Right? No corners, because this is a polynomial function. That's just a guide based on my end behavior. Okay, just so I know. It doesn't have to be there. Okay. Okay. So here we go. Find the polynomial function. So look, of degree n with only the following real zeros, more than 1 is possible. Okay, so look. First of all, we want a polynomial function. That means we have to write it in function notation. So f of x is equal to, if 6 is a 0, then it comes from a term x minus 6, right? If 3 is a 0, it comes from a term x plus 3. Now, when I multiply this, it'll have a degree of 2. But I need it to have a degree of 4. So I have, we could square both of them. What else could we have done? Not 4 on one of them, because then it'll be 5. 3 on one of them. So x minus 6 cubed, x plus 3. If I make this a 1 and add another x, that won't work, because then I'll have another 0, x equals 0. So that's not going to work, right? I mean, or you could have x minus 6 to the 1, x plus 3 to the 3. So there's definitely more than one possibility. No, that would give another 0. You can't. Exactly. You can't do this. Right? You can't do that. Okay? Yeah. It doesn't say. There may be, but it doesn't say. This is all the information we're given. If we had more information on the multiplicities, then we could determine what the exponents could be. Okay? But look at this next one. This next one is a little bit more concrete. So first, let's determine the least possible degree and the end behavior. So first of all, the end behavior here, because it's like they're both negative infinity, they're the same. The leading term for this, is the degree for this going to be even or odd? Even, right? So that we already know. So 2, 4, 6, and so on. Now it says the least possible. How many turning points are there? 3. So the least possible degree would be what? Right, 4. And then the end behavior, the limit of f of x as x approaches negative infinity is negative infinity. And also at positive infinity is negative infinity. Okay. They're both negative infinity. Locate the zeros and state their multiplicity. Assume all of the zeros are integers. Okay, so what's 1 0? Negative 3. What's the multiplicity? 1. And then let's just say 2, also multiplicity of 1. And then x equals, what's the next one? 6. That has a multiplicity of 2, right? Because we're going with like the lowest one. Okay? Like they could have also been like 3, 3, and like 4 or something, but we're going with the lowest possible number. Okay? Yeah.
For finding the least possible root, would you use the
Yeah, turning points plus 1.
So you wouldn't use the zero?
No. Turning points plus 1. Yeah.
How would you have any multiplicity?
Because it turns around. It would just be multiplicity of 1. But the fact that it turns around, it's an even multiplicity. Okay, so now create a function that fits the graph and the given point. This time we've been given a point. So here's how you're going to do it. You're going to say y equals a, remember the a? X plus 3, x minus 2, x minus 6 squared. Okay, but now this point that I'm given is x and y. So I'm going to plug that in. So y is 64 is equal to a, and then we're going to plug that in here. What was the x? Negative 2. Okay? So then I get 64 is equal to a times 1 times negative 4 times what? 64. Yeah? So the 64s divide. So that'll be 1 equals negative 4a. So a is negative 1 over 4. All right? So now I say f of x is equal to negative 1 over 4, x plus 3, x minus 2, x minus 6 squared, and that's my function. Right? Down to the t. Yeah.
Like, there's no way of determining a unless you do that.
Correct.
And a doesn't really say anything about keeping or off. That's just that.
Correct. That's just exactly that is what determines, like how high and low these are going to be and what points they're going to pass through. All right? So that's this. Okay. So lots of